hope you recollect what we are doing on this topic. Let me quickly remind you of some of the things that we have learned, so that you are at least on the same wavelength that I am going to talk on. We discussed the noise performance of AM systems, first for the case of synchronous demodulation, right, and we found that in this particular case the signal to noise ratio was given by the expression output SNR was given by this kind of an expression, right, where this is average message power, this is the carrier amplitude, and this of course is worse than what you get when you have DSPSC, when you use DSPSC. This is DSP AM with some percentage modulation of some modulation index, arbitrary modulation index, and we found that there is a reduction in SNR by this factor because of the inefficient use of the carrier, inefficient use of the transmitter power. But other than that, the fact was that the output signal to noise ratio was linearly dependent on the input signal to noise ratio. Then we perform these, we consider the case of demodulation of the AM signal via envelope detector, right. We consider the noise in this situation again, and we found that the same expression is still valid, right. The same expression for SNR is still valid, provided that, what was the condition under which it is valid? Provided that noise is comparatively small compared to the carrier, right. That is, A plus MT is much greater than NIT or the quadrature components NCS, NCT and NST for all t. That is, if for all time or most of the time the noise remains much smaller than the signal amplitude, by signal here I do not mean just the signal, but carrier plus signal, right, then we get the same expression for the output SNR. So, there is no difference in the performance of a synchronous demodulator or an envelope detector under small noise conditions. The performance is identical. Then we are considering this other extreme, when noise takes over, that is, when the opposite is true, when A plus MT is much less than these two things, that is, the signal is much weaker than the noise, right, and under this condition we have obtained an expression for the envelope of the output signal, which was given by, let me just recap how did we obtain this expression. The exact expression for the envelope was the in phase component, which is A plus MT plus NCT whole square plus NS square T, right. This is the exact precise expression for the envelope with no approximation. When you make this assumption of A plus MT being much less than this, right, basically what it means is that when I expand this term here, the square of A plus MT can be ignored, because that is going to be much smaller than either NC or NS, right. So, we can write this as, if I ignore those square terms, this will be NC square T, that will be the term coming from here, plus NS square T, that is a term coming from here, and then we also cross product term, right. I have only ignored the term A plus MT whole square, because that we are assuming is much smaller than NCT, right. So, the cross term will be 2 NCT into A plus MT, correct. Okay. Now, denoting by En square t, the quantity Nc square t plus Ns square t, which gives you the instantaneous envelope of the noise alone, right. Then we can write this as square root of En square t plus 2 Nct into A plus Mt, right. Again, if I take Ent outside this, right, I will be left with 1 plus 2 into A plus Mt into Nct upon En square t. Okay. Now let us look at this last quantity, particularly let us look at the quantity Nct upon Ent. Consider this ratio. Let me just draw your normal trigonometric thing. Let us say this represents your Ns, right. This represents your Nc. Then this will represent your Ent, and this will represent your theta Nt, where theta Nt is the instantaneous phase of the noise part, right. So, can I express this ratio in terms of theta Nt? It is tan inverse, it is cosine, sorry, sin theta Nt, sorry, cosine theta Nt, alright. So, this will be, we can therefore write this part as your instantaneous envelope becomes Ent into square root of 1 plus 2 A plus Mt upon Ent, one of the Ent's will stay, into cosine theta Nt. Okay. So, that is the expression that we have for the instantaneous envelope. We once again use the approximation that A plus Mt is going to be much less than Ent. Ent is a noise amplitude, right. A plus Mt is a carrier plus signal amplitude, which we are assuming to be much smaller than the noise amplitude, right. So, once again if we use that approximation, we can write this, we can carry out a binomial expansion of this square root, right, and return only the first term, and you will get Ent. This is approximately now equal to, of course this was also approximate because we had made a small signal approximation. So, this will become Ent into 1 plus A plus Mt upon Ent into cosine theta Nt, which you can write as Ent plus A plus Mt into cosine theta Nt. So, what do we see from here? That is the final expression that we are looking for. Your instantaneous envelope is this, which means your envelope detector will produce this kind of an output, right. Whereas, what is it that you would like to see? You would like to see something proportional to Mt. Unfortunately, in this expression you do not find any term which is a constant times Mt, right. Right. It is not even that you have something constant times Mt plus something. The plus something we could have considered as noise, and you would have signal term, and you would have noise term, and you would have calculated a signal to noise ratio. What you get out the output is almost entirely noise, right, because this is pure, this is a noise envelope, right. So, this is noise, nothing to do with the signal. This is also noise, right. This of course is getting multiplied with Mt, but that does not help, that is still noise, right. If signal Mt which is multiplied by a noisy waveform will be some noisy waveform. So, it is not even signal plus noise kind of an expression. So, essentially the envelope is almost totally noisy, right, with no component which you can consider as being proportional to the message MT, which is our desired signal. Right. So what does it mean? That means under large noise conditions, the envelope detector fails to deliver a signal of interest. It completely breaks down. Right. Now, how does that compare with what the synchronous detector would have done at this condition, at low SNR, in the large noise conditions? The synchronous detector, when we derive this expression, right, when we derive this expression for the case of synchronous detector, we did not have to make any assumption whether the signal is small or large. This expression was valid for all conditions of signal and noise. Right? Please remember that. Which means if I were to plot for the case of synchronous detector a plot of the output SNR versus, let's say, gamma, right, where gamma, if you remember, is SI upon NB, right, the signal to noise ratio of the input in the message bandwidth. Right. Then what would this curve be like for the case of synchronous demodulator? It's a straight line with a slope given by this expression. Right, it's a constant slope, and it will pass through origin. Right, so it's a straight line curve like that. You agree? So what does it show? That even here, when the input SNR falls down, that is when the noise becomes large, the output SNR will of course fall down. That is bound to happen. Nothing we can do about that. But the falling down is very graceful. Right? It is a linear falling down. But what do we find now? Our finding now is that as the noise becomes, in the case of envelope detector, as long as the SNR is high, that is you are in this kind of region, let's say above some value, right? If your input SNR, if your input signal is much stronger than the noise, you are more or less on the same curve, right? Because the two expressions are same. However, the moment you fall below a certain input signal to noise ratio, right, when the input signal becomes weaker than some value, or the input signal to noise ratio falls below some value, you start deviating from the straight line curve, right, and you start moving down. Eventually, at lower SNRs, you get a signal which does not resemble the we get an output which does not resemble the input at all in terms of message, right. So you get a curve like that. Incidentally, you should have asked me what is the negative axis here denote. I am plotting this in decibels, so you can have negative dB value as well as positive dB value. Of course, signal to noise ratio in absolute terms will always be positive because it is a ratio of powers, but when you take it in decibels, you can have negative value of the signal to noise ratio because it is 10 log of the actual value, right. So this is what it happens. This is the behavior. So this is what you are going to see in the envelope detector, and this kind of phenomenon that is exhibited by this envelope detector is called the threshold effect. Right. Basically, what the threshold effect says is that the output SNR does not degrade gracefully as the input SNR is reduced. Right. Below a certain value of the threshold, let us say below this value, you find that the output SNR degrades much more than the input SNR degrades. Right. If it had degraded by the same amount, you would have been on this straight line. Right. So it degrades much more, and therefore there is a concept of some kind of a threshold value of the input SNR, and you must operate always above the threshold value, right? Because if your receiver operates below the threshold value, rest assured that you will get a very bad, highly mutilated output, right, which will not resemble the signal at all. Fortunately, this particular effect is not that important in typical broadcast applications in amplitude modulation. The reason being that the value of the threshold SNR at which this will start to happen, I will just give you some figures, is of the order of 10 dB, right. That means unless my input signal to noise ratio falls below 10 dB, I will continue to be more or less on this linear curve, right. And typical acceptable values of the signal to noise ratio in broadcast applications is anyway much larger, right. Typically, so gamma typical, if you remember I discussed this earlier with you, will be greater than 30 dB or like 40 dB, right. So which is much more than this, because this in absolute terms is about 1000, right, and this in absolute terms is about 10, right, isn't it? So since the typical values are going to be much larger than the threshold value, you will never see the threshold effect in typical radio receivers, because you are typically operating at input signal to noise ratios which are much larger than the threshold value at which this phenomenon will start to be seen, right. So that's a point of comfort that fortunately for at least broadcast kind of applications, it doesn't, this we can still use the, what was the motivation to use the envelope detector? The motivation was to simplify the receiver, but at the same time we don't want to lose in performance. This says that you will lose in performance, but fortunately that loss of performance comes in those regions where it is not important. We are not going to use those regions at all in typical applications, right. So it doesn't matter, so the simplicity can still be kept without much loss. Okay, that's the lesson that we learned from this. Any questions? One of the issues that arises here is, how do we calculate this value of 10 dB or whatever it is, the so called threshold SNR, right. So I will just give you a brief indication. We will not go into a very detailed discussion of this, but I think you should have some feel for how do you calculate this SNR at which this starts to deviate significantly from the straight line curve, right. Now this point of course is arbitrarily defined in some manner, right. You could define it here, or you could define it here, or you could define it here. You have to just agree on some definition and do the calculation accordingly, right. So what we will do is, we will define the point of threshold in a particular manner and then calculate at what SNR, input SNR, that point of threshold will occur, right. So let us look at a very typical calculation of the threshold SNR. You understand the meaning of gamma threshold? Gamma threshold is that value of SI by NB such that below this you will start seeing significant deviation of the output SNR curve compared to the linear curve, right. That is the definition. Now we can do this calculation by looking at, by talking in terms of probabilities, right. So we talk about, okay, let me first give some important results which hopefully you should know by now if you have reviewed your probability theory properly. The probability distribution function, let us consider the probability distribution function. Actually I should talk about small PDF, the probability density function of the noise envelope. ENT is a noise envelope, if you remember, right. And how is the noise envelope expressed in terms of the quadrature components? It is this. You are working with Gaussian noise, right. Your NIT is given by NCT cosine omega CT plus or minus NST sine omega CT, right. So this is Gaussian. What else do you know? That this is also Gaussian. These two quadrature components are also Gaussian, right. If you have done the review properly of probability theory, then you would know that when you take the sum of squares of two Gaussian random variables, right, and take the square root of that, then the resulting random variable is not a Gaussian density function. It is Rayleigh. It has a Rayleigh density function, right. So, if you have not reviewed this, please review it, right. So, given that the density function of NC and the density function of N sub S, let us say, are Gaussian, 0 mean Gaussian random variables, right, assuming both NC and NS have both 0 mean and variance sigma square, right, then it is very easy to show that. So, if this is given, then the density function of En, right, the density function of the instantaneous envelope will be given by this expression. Okay, for alpha greater than 0. Obviously, this has to be a positive value always. So, this density function is defined only for positive values of the argument, right. ENT has to be always positive, and that is the Rayleigh density function. Okay. Incidentally, what will be sigma square in this case? Sigma square is the noise variance of NC or NS. That will be the same as the noise variance of NI, and what is each of them is equal to 2NB, if you remember, isn't it? This is the noise variance of the narrowband signal which is coming out of the band pass filter before the envelope detector, right. What is the bandwidth of that filter? 2B. What is the noise pass pixel density height? N0 by 2, N by 2. So, N by 2 into 4B, 2B on the positive frequency side and 2B on the negative frequency side. So, sigma square is the noise variance, which is the power in the noise signal, which is the area in the power spectral density function, which is going to be equal to N by 2 into 4NB, right. So, sigma square is 2NB in our case. Is this calculation understood? Good. So, this density function looks something like this. If you do not know it, I am sure you know it. The Rayleigh density function, the Gaussian look like that, right, the 0 mean Gaussian. The Rayleigh density function, since it is going to exist only for positive values of alpha, will look something like that. Okay. So, that is a Rayleigh density function. Okay. So, that is a little bit of the background that is needed. Now, let us come back to our threshold calculation. This was just to review one of the important results which is required for us to do the threshold calculation. Right. So, we have to define the threshold. We will say that if, so we will say threshold occurs if En, the noise amplitude, the noise envelope becomes greater than the carrier amplitude A with a probability of 0.01 or more. Basically, if the probability becomes 0.01, so now we would like this noise to be much smaller. When the noise is much smaller, the probability of this exceeding this would be very small, right. What we are saying is, if the probability of the noise amplitude exceeding the carrier amplitude becomes 0.01, right, that is the point at which we will say the threshold has started. This is an arbitrary definition. You could have changed this, you could have made this 0.1 if you wished, right, or 0.05. So, depending on what probability value you fix here, the resulting value of gamma threshold will be different, right. So, this is just something arbitrary that you have to fix and then calculate according to that. So, basically what we are saying is that if noise amplitude is greater than the signal the carrier amplitude with this much probability, right, if the probability of this happening is 0.01 or more, right, then the threshold phenomenon, you are in the threshold region, right. So, this is the point of threshold at which that is what we need to understand. So, what is the corresponding signal to noise ratio which will result in this kind of a situation, right, that is what we need to calculate. Okay. So basically what we are saying is, okay, if this is your probability density function curve, this is basically the probability of this is the density function P E n alpha, right? So what we are saying is, this is the area under this tail of this curve gives you this probability where this point is A, right? So when this area is 0.01, that is the point of threshold. Okay. So what we are saying is, if you look at the probability that E n is greater than or equal to A, that will be this area, that will be given by the integral from A to infinity of this Rayleigh density function alpha by sigma square e to the power minus alpha square by 2 sigma square d alpha, right. This is a very simple integral to evaluate. Its value will be e to the power minus a square upon 2 sigma square. It's actually very trivial, and this is going to be equal to, this probability we are saying should be equal to 0.01 at the point of threshold. Is that clear? We are defining that, defining our threshold point to be the point at which the probability of this event becomes equal to 0.01, right. Now from this we can calculate what is the corresponding value of a square by 2 sigma square, right. So that means a square by 2 sigma square should be the natural log of this, right, and that turns out to be 4.605. Okay. Now since your sigma square is 2 MB, this means your a square by 4 MB is 4.605, right. Now let's talk in terms of input. What is it that we want to talk about? We want to talk about SI by MD. What is SI in our case? SI, if you remember, is a square plus m square t, average value of that, upon 2. That's the received signal power. That's the carrier power plus the message power, right. Let's assume that your, for the sake of simplicity of calculation, that MT is a tone, pure sinusoid, right, and let's assume that modulation is 100%. If the modulation is 100% and MT is pure tone, what is the amplitude of this pure tone? What is the power in m square, maximum power in m square t? A square by 2, right. So this will be a square plus 0.5 a square upon 2, which is 3 a square by 4, right. So what is the value of gamma threshold now? That is SI by NB. This is 3a square. SI is 3a square by 4, right, but the value of a square by 4 NB is 4.605, right. So this becomes 13.8, or in dBs this is 11.4 dBs, which is consistent with the figure I gave you a few minutes ago. I said approximately 10 dB, right. So this is typically how you will do the threshold SNR calculation. Is this understood? Any questions?
So on what basis the value of probability was chosen to be 0.01?
Arbitrarily, I told you.
But sir,
Right?
then
It's a matter of defining. You agree on some definition, because otherwise at which point it starts, it's really very difficult to say in that sense,
so
right?
it is standard.
This is more or less standard, right? You agree on some definition, that's all. Okay. Basically what I said is, the point, the idea is to say, okay, at this point there is a significant probability that you will get away from that linear curve, right? You will get away from the linear curve by a significant amount. So, I think that brings us to the end of the discussion on noise in amplitude modulation systems. So, we discussed all kinds of amplitude modulation, DSPSC, SSB, VSB, synchronous modulation, then DSP AM with carrier, both synchronous and non-synchronous demodulation, right. So, more or less that exhausts the same picture. What are the various messages which we can summarize at the end of this discussion? Message number 1, the SNR performance of practically all synchronous modulation schemes barring the one with carrier are the same. Output SNR is the same as the input SNR in the message bandwidth, right. There is no difference. They are all same in terms of SNR performance. They have pros and cons in terms of bandwidth and other issues which we have already discussed, but in terms of noise performance they are all equivalent. That is message number 1. Message number 2, when you have non-synchronous demodulation using an envelope detector, you get a performance loss corresponding to the power loss that is embedded or implicit in the use of these modulation schemes. Nothing surprising there also, right, because not all the power is being used to convey the message signal, right. Some of it is just transmitting carrier which contains no intelligence of its own. So, therefore, you get an SNR reduction by that factor. Third message, there is again no difference between the performance of a synchronous detector and an envelope detector as long as noise is sufficiently low. However, when the noise is lower than a certain higher than a certain value, you can see a threshold phenomenon in the envelope detector, not in the synchronous detector, right. Synchronous detector continues to perform with the same expression for output SNR. Of course, output SNR degrades as the input SNR degrades, but it degrades linearly. We say it degrades gracefully, okay, whereas now it is degrading not so gracefully, okay. Okay. So, next thing we obviously need to do is look at noise in angle modulated systems. Okay, what is our model now? Our model now is as follows. At the modulator, at the transmitter, we have the message followed by an angle modulator. Right? Then you have the channel which introduces noise. Okay. At the receiver, at the front end, you select your signal of interest using a band pass filter. This is followed by the angle demodulator. Okay. And finally, you will have a baseband filter whose bandwidth is the same as that of the message signal. And you are interested in calculating your output SNR by calculating the output signal power and the output noise power. So, that is your transmitter, that is your channel, this is your receiver, and that is your model which you have to use for doing your SNR calculation. Before we proceed on to the calculation, just a couple of remarks to keep in mind. We can't exactly proceed the way we proceeded for amplitude modulation for two reasons, right. One is that the band pass filter here has a very different bandwidth as compared to the band pass filter that we had at the input to the amplitude demodulator. Do you appreciate that? Because your angle modulated signal has a much wider bandwidth. Of course, we are considering a wideband FM, isn't it? It has a much wider bandwidth. So, the band pass filter, if you want to ensure that your angle demodulator receives an undistorted angle modulated signal, it must ensure that most of the significant frequency components of the modulated signal pass through. So, whatever is the bandwidth of this signal that is coming out must be allowed to pass through. through this band pass filter. So, the bandwidth of this message band pass filter is not 2B. If B is the bandwidth of MT, this is much more than that. It will depend on the peak frequency deviation of your angle modulator, right. That is one difference as compared to the AM signals. It will have some implications which you have to understand. The second complication is the amplitude modulation systems were linear, at least when you are discussing synchronous demodulators. It became non-linear when you are discussing angular detectors, because then there is a square root operation and things like that happening, right. But otherwise they were linear systems. That means we have actually used the principle of superposition. That is, we assume that if I calculate the effect of signal at the output and the effect of noise at the output, I can do that separately, right, independent of each other. I can calculate, okay, this is the input signal power, what is the output signal power? If this is the input noise power, what is the output power, noise power, and then take the ratio, right. Linearity implies that the ratio will be just the same, right. I can't do that anymore. It's not a linear system. So, these are the two complications that we have to take care of in the analysis of angle modulated systems. Okay. So, let us proceed. Let us start with our modulated signal S of t, which is here. S of t is here. Okay. This has a form A cosine omega ct plus some waveform psi of t, which contains your intelligence, right, where the waveform psi of t is equal to kp k sub p times mt if you are working with phase modulated systems, and it will be k sub f times mt integral of mt when you are working with frequency modulated systems, right. MT is the message. This is the model with which you have to work now. So, let us start from the very first point. You have white Gaussian noise being added on the channel. What kind of noise you see here? Once again, narrowband noise, but this narrowband noise has a bandwidth much wider, right. So, at the demodulator input, always look at the noise at the demodulator input. That is a key thing, right. The noise with n sub I t, when I say I, it refers to input, but what point in the demodulator, what point in the receiver? After the band pass filter, input to the demodulator, right. Remember that. So, this again can be written as NCT cosine omega Ct plus n sub St. So, there is no difference here as far as the representation goes. Representation is still valid, right. It is a narrowband noise process, it will have this representation. So, it is a band pass signal, band pass process with a power spectral density function, which we can denote by Sn omega. The important thing is that this power spectral density function will have a bandwidth which is equal to twice delta f plus b, isn't it? Carson's rule. The delta f is the peak frequency deviation of your modulator, whether it is FM modulator or PM modulator, right. Alternatively, we can also write n sub I t in terms of its envelope ENT into cosine omega Ct plus theta nt, right, where ENT is square root of Nc square plus Ns square and theta is tan inverse of Ns upon Nc. Or you can write other similar equations. Let us first consider phase modulation. And before we proceed, one point I like to you to understand what is the implication of the fact that your noise has this bandwidth. whereas your signal, what is a signal? By a signal I should say message actually. A message has a bandwidth of B. So MT has a bandwidth of B, but the noise that you are considering at the demodulator input has a much larger bandwidth. Typically delta F is much greater than B, right? Now
So but we are passing it to the filter, right? Band pass filter.
yeah.
To depend the noise, well, if I have a very large section for the noise, the thing which I am inputting at the demodulator will depend upon the band pass filter, that is the bandwidth of my filter.
Yes, that's precisely what I am saying. This is the bandwidth of this filter is going to, I mentioned this earlier, you have to ensure that the bandwidth of this filter is equal to the bandwidth of the FM or PM signal. If you don't ensure that, your angle demodulator is not getting the right kind of input for demodulation, right? So the bandwidth of this filter has to be equal to twice of delta F plus B. That's precisely the point. Whereas the bandwidth of message is B. That's all I am saying. Message signal has a bandwidth of B. MT has a bandwidth of B. The signal which is going, the noise and signal which are going into the angle demodulator, both of them have a bandwidth of twice delta F plus B. That's all I am saying. So I am not saying different from what you are saying. What is the implication of this? The implication of this is as follows. Look at the signal part. This signal also has the same bandwidth. The signal that is reaching here also has the same bandwidth. Noise also has that bandwidth. But the message is not embedded in ST. Message is not ST. Message is in SIT. Right? That has a bandwidth of and simply B. What it means is, to this you are adding noise, right? What you are seeing here is not only this but this plus noise. So, and that's the important point to note now, to understand that if I look at the sum of these two things, this signal plus this noise, this has a very large bandwidth, this also has a large bandwidth, but this has a small bandwidth, right? Now therefore this will fluctuate very quickly.
So
The
from where E came?
ENT,
We are adding it.
cosine theta, NT, whatever. Think I'll let me write separately. So at the input to the system, the signal has an instantaneous amplitude which is constant A and instantaneous phase which is psi of t, right? The noise has an instantaneous amplitude which is ENT and has an instantaneous phase which is theta nt. I am basically trying to compare these two. This is what you have to understand. A is anyway constant, right? A is the amplitude of the input signal, right? Modulated signal. Psi of t is proportional to nt. For phase modulation, psi of t is kp times nt, right? Now what we are saying is ENT, which is the instantaneous amplitude of noise, and theta nt, they will be having a bandwidth proportional to delta F plus B, right? So they will vary much more rapidly than psi of t. This is the important point. Since psi of t has a bandwidth of B and each of these has a bandwidth of delta F plus B, isn't it? These are low pass signals. The band pass signal had this bandwidth, the corresponding two low pass signals will have this bandwidth, right? NCT is ENT cosine theta nt and NST is ENT sin theta nt, right? So these two signals, the envelope and the phase of the noise, will fluctuate much more quickly, much more rapidly than the phase of the signal of containing your intelligence, right? Than psi of t. That means you can think of the phase of the phase of the carrier which contains a signal, which contains a message, more or less remaining constant over several cycles, whereas the corresponding phase of the noise would have undergone very wild fluctuations in that instant, in that period, because let's say over a small period of time, value of psi t is nearly constant. The carrier goes through many cycles. Over many cycles of the carrier, the value of psi of t is nearly constant, equal to some kp times mt,
Sir,
right?
isn't ENT and theta NT both low pass?
They are low pass, but they are low pass with a much wider bandwidth, right? This is also low pass. This has a bandwidth of b. I am comparing two low pass signals, right? And three low pass signals actually. This is mt, right, which has a bandwidth of b, and these are the noise. These are much, their bandwidths are very different, so their properties are different. That's the point I am trying to really say. These will fluctuate more rapidly, this will fluctuate less rapidly. This is a point to keep in mind as we proceed. Okay. Now how do we calculate the output SNR? We cannot use the linearity principle. I cannot consider signal alone and noise alone, but I will use this fact that I just discussed. And the best thing to do is to start with looking at the sum of these two, which is what you will have at the demodulator input. And the demodulator input, what is going into the system, the demodulator, is cosine omega ct plus psi of t plus nit, which you can write as a cosine omega ct plus psi of t plus ent cosine omega ct plus theta nt. Right? Now to proceed further, it is best to understand the nature of this signal, this edit signal, this sum, through the phasor diagram. Now the phasor diagrams that we discussed earlier are going to be very important now, very useful to carry out this analysis. Let's remember the basic points. This is your reference phasor, right? At some time, at the time instant t, what is the instantaneous carrier phasor? Omega ct plus psi t, right? So let me denote that by this. This is omega ct plus psi t. If you are assuming that the whole system is rotating at omega c radians per second, then you can simply write psi of t, right? Otherwise you write omega ct plus psi of t. This has an amplitude of a, right? To that you are adding this noise, which has an instantaneous amplitude of En and has an angle of theta n with reference to the reference phase. So let me denote that by this has an amplitude of En t, and this angle is omega ct plus theta n t. Agreed? So what we are seeing is the vector sum of these two, right? And the vector sum of these two will be this, right? Let me call this vector sum as RT, or actually it is YIT, it's the same thing. So the amplitude of the vector sum is RT. So therefore I can write YIT as having it has an amplitude of RT, right, which is this plus this sum of these two vectors into cosine of omega ct. It's a phasor whose instantaneous angle is omega ct plus psi t, and let me call this angle as delta psi of t, right? So it is psi t plus delta psi of t. It is clear that the effect of noise is now where? Where is the effect of noise going? It is going in RT to some extent and in delta psi t, right? If this noise was not there, this delta psi t would have been 0, right? Is this clear? The time variation in this would not matter, because if you remember, the demodulator will also contain a limiter, right? So this will be converted into a constant amplitude. This is of no consequence. Really speaking, the angle demodulator will produce an output proportional to the instantaneous angle. So the effect of noise will be obtained by considering the effect of noise on delta psi t, because that is what you should not have got, which you are getting because of noise, right? And as you can see, this is it's a not a linear analysis. Okay. Once again, to proceed further, we have to consider two situations separately: the small noise case and the large noise case. Right. So let's quickly consider the small noise case, and then we'll look at the large noise case in the time permits. Okay. We may not be able to complete it, but let's write a few expressions. So let's first consider the small noise case, defined as the situation where the noise amplitude is for all times much smaller than the carrier amplitude. That's the definition of small noise case. Now, what in terms of phasor diagrams, what does it mean? We are saying that this amplitude is much larger than this. So what basically it implies that this angle delta psi t would be very small angle, right? So we can use all kinds of interesting approximations under that situation. So this, therefore, we say is that this will imply that delta psi of t will be much less than pi by 2 radians for all time. Okay, and if you were to just imagine, let's extend this. I can write an expression for delta psi t. If this angle is very small, I can approximate it by let's say sin this upon this, right? And this amplitude, the length of this line, you can, if this is really very large, this length is very small. Basically, this, because noise is very small, this angle is approximately the same as this angle, right? Assuming that this length is very, very small. So these two lines become parallel at this point, more or less. We consider a very extreme situation. So in that case, what can we say about this length of this perpendicular here? It is ENT into cosine of this angle, isn't it? Sorry, sine of this angle. So therefore, you can write approximately under this situation delta psi of t as equal to ENT sine of, and what is this angle incidentally? What is this angle? It is this angle minus this angle, right? So it is theta nt minus psi of t upon A, right? So I think this is a good point to stop. We will start from this point onwards and try to understand the output SNR in terms of this expression. Okay. Thank you very much.